In this video, we start looking at linear regression. In particular, we're going to introduce the ideas of fitting a line, residuals, and correlation. This is my overview slide, which I'll spend about 5 minutes going over before going over each of these topics in more detail and with more examples. Our first topic will be fitting a line to data. So we have a set of data that has a variable y, which depends on a variable x, and we want to be able to predict y based on x. If we have a linear relation, we can write this equation: y equals some constant b naught plus another constant b1, which is called slope, times our variable x, plus e, which is our error. So b naught and b1 are parameters, e is the error, and sometimes omitted. You should be familiar with this form from algebra, y equals mx plus b, where m is the slope and b is the y-intercept, where we intercept the y-axis. So we use the predictor explanatory variable x to predict the response y. We have the concepts of residuals. Because our line may not perfectly fit the data, the leftover variation in the data after accounting for the model fit, that is, data equals our fitted line plus residuals. The residual of the ith observation, x sub I, y sub I, is the difference between the observed response, y sub I, and the predicted response, y, given by our line. If an observation is above the regression line, then its residual, the vertical distance from the observation to the line, is positive. Observations below the line have negative residuals. A goal of picking the regression line is for the residuals to be as small as possible. The size of the residual is discussed in terms of absolute value. Finally, we'll look at correlation, which is a measure of the strength of a linear relation. So correlation, which always takes a value between -1 and 1, describes the strength of the linear relationship between two variables. We often denote the correlation by the letter R. So when the relationship is perfectly linear, the correlation is either -1 or 1. If the relationship is strong and positive, the correlation will be 1. If it is strong and negative, the relation will be -1. If there's no apparent linear relation, the correlation will be near 0. So I have this chart here to give you some examples. So R equals 1 and R equals to -1 are perfect lines. It's when our data perfectly fall on a line. When R is positive, the line slopes upwards. When R is negative, the line slopes downwards. As we go from 1 to 0, we still have this upward slope, but the closer we get to 0, the more and more the data starts to fall off the line until it becomes a fairly loose collection of points. Similarly, when we go from -1 towards 0, the line becomes less and less defined until we get sort of a loose collection of points vaguely pointing downwards. So again, as you get close to 0, you have no correlation. At 0, it's just a bunch of scattered plots with no apparent line. As you go closer to 1 or -1, you get more and more linear. It's important to know that there are non-linear relations that are possible. So a low linear correlation does not necessarily mean weak association. And this is our graph to illustrate that. Here you see there's this R value that isn't very high. It's not that close to 1. It's sort of close to 0. But there's this clear relationship between the data, like you've got this kind of parabola form. But this is not a linear relationship. It's not a line, which is why the correlation coefficient R is relatively low. Here again, you have a relatively low correlation coefficient, but you can see the line kind of does this little cubic kind of shape. Here you have a relationship of 0.5, sort of strong. There's no line in here, but you can kind of see there are little clusters of data. They're kind of, related, but it's a weak linear correlation. That concludes our overview, so we'll come back over here, take a closer look, starting with fitting a line to data. So when we fit a line to data, the model we're going to use is our variable y is equal to some parameter b naught plus another parameter b1 times our variable x plus an error. We're generally going to admit the error. And this form is familiar to you from algebra, the y equals mx plus b, where m is the slope and b is the y-intercept. And I cannot resist to review the algebra here, even though it's really not covered or going to be important in your book. But y equals mx plus b, m is the slope, b is the y-intercept. I'm going to give you an example so you can see what this is, just to review. And again, in terms of this formula with the b0 and b1, then b1, that's what multiplies your variable x. So b1 is your slope. Your b0 here is by itself. That's your y-intercept. So the example I'm going to give you is y equals 2/3 x plus 1. And the easiest way to plot this is just to plug in some points for x. And I plug in small values and whole numbers because it's easier to work with. And then once I plug in x, I calculate my value for y. So x equals -1, that's 2/3 times -1 plus 1. Here we have 2/3 plus 1 is equal to -1/3. When we plug in 0 for x, we just get 1. When we plug in 1, we get 2/3 times 1 plus 1, which is 1 and 2/3. When we plug in 3, that's 2/3 times 3, which is 2, plus 1 is equal to 3. Okay, so now we can plot. Our first point, which I'll do in blue, is x equals -1, y equals -1/3. So here x is -1, y is -1/3. So we're here at this blue point. Then we have x equals 0, y equals 1. So x is equal to 0. We go up 1 for y. So that's going to be my green point. I put my dots beforehand because first I tried to freehand it and the line wasn't that straight. Anyway, so 1 and 2/3, so 1 here and then 1 and another 2/3, and then finally 3 and 3, that's our red dot. So this is yellow. So our red dot is 3, 3. So you can see our line. I still didn't draw a very straight line. Looks something like this. Sorry, it's not straighter. So, this isn't drawn very well. I think this part looks better. So let's look at what I mean by slope and y-intercept. So first, this y-intercept is where our line crosses the y-axis. So you can see it crosses at y equals 1. That's where x equals 0, y equals 1. So that's our y-intercept. And then second, our slope 2, 3, this is positive. That means for every 2 units you increase in x, so every 2 units you go to the right, you're going to, because this is also positive, you're going to increase y by 3. So every 2 units, so let's go up 2, we're going to increase y by 3. So we get this red point. So for 2 points, if we start here, we can have 2 points, we can draw a line. Okay, that's it for our little algebra tangent. It's rare for all the data to fit perfectly on a straight line. Instead, it's more common for the data to appear as a cloud of points. So let's look at this. So this is a pretty strong line. You can see it's sloping downwards. In other words, as x increases, so as we go this way on the x-axis, you can see the values for y kind of tend to go down. So they move in opposite directions. But it's a pretty strong line. So this is a fairly highly correlated when just using the word correlation from our overview slide. Here, it's a little less correlated because the cloud is a little looser, surrounds the line a little loosely. But there's a moderate trend going upwards, right, as we get bigger values of x. So like, let's compare 2 values of x, like maybe this value of x here to this value of x here. You can see the y value also tends to increase. So it's a moderately upward trend. Of course, not every value of x is going to be this way. Like here's a fairly low value of x, right? The x-axis hits fairly low, but it hits the y, higher than this value of x, which is higher. So it's not 100% as x goes up, y goes, as x goes up, y goes up. But for the most part, that is the general rule for these points. Finally, we have this. This is a very weak linear trend. It's almost just like a cloud of points, not much of a line. But also there's not much of a, as x increases, y increases, no strong downward or upward trend. So kind of maybe a straight line, but it's weak. And then also something we want to know here is data for values of x. This is value y, and this is hitting a ball, I think. So like the angle that you hit a ball at, this is the distance it travels. So the larger the angle, the more distance it travels. At some point it starts to decrease. But anyway, so this is a perfectly like there's strong association, like you can see that there's some formula for this. It's the formula for some parabola, but it's not a line. So it's clearly related, but not linear. So let's do an example from your book. Bush-tailed possums are a marsupial that live in Australia. Aren't you happy you learned this? Okay, researchers captured 140 of these animals and took body measurements before releasing the animals back in the wild. We consider two of these measurements, the total length of each possum from head to tail and the length of the possum's head. The figure below shows the scatter plot for the head length. Here's the head length and the total length of the possum. So you kind of figure if the bigger the possum, maybe the bigger the head. Each point represents a single possum from the data. So like here, we have a possum whose length is above 85 but below 90. And the head circumference is somewhere over here around, I don't know, 88 millimeters. And it looks from this data that the head and total length variables are associated. Possums with above average total length also tend to have above average head lengths. I think the average might be, I'm not sure where the average is shown, but it trends upwards. While the relationship is not perfectly linear, it could be helpful to partially explain the connection between these two variables with a straight line. Our next topic is of residuals, which you can think of those are the leftovers after accounting for the model fit. So in other words, our data is equal to what's on the line plus the residuals. It's kind of like the error from that is how much the data varies from our line. So the residual of the ith observation, x sub I, y sub I, is the difference between the observed response, y sub I, and the predicted response, y. If an observation is above the regression line, then its residual, the vertical distance from the observation to the line, is positive. Observations below the line have negative residuals. And this is important. A goal of picking the regression line is for the residuals to be as small as possible. This is how we measure how good that line fits. It's basically we want the residuals or the errors to be minimized. And the size of the residual isn't discussed in terms of absolute values because you don't want the negative residuals canceling with the positive residuals. So here is our example, which looks super busy, but it's not that bad. This is our line for the possum body length and head. So here's our line, and here's our point X, our actual data that says that a possum with a body length of, 77 or something, has a head, whatever measurement of 85, whereas the line would predict something a little bit bigger, like 86 or something. So this measurement is below the line, so this line needs to be adjusted by a small negative residual, -1. So yeah, if we predicted 86 and the actual is 85, the residual is -1. Over here we have this plus sign. This is our next one. It's actually a pretty large residual because the line for an 85 total length body length predicts something right over here, a little over 90, but the actual data point for this one data point is way over 96. Maybe this is an unusual measurement, but this measurement is not. It has a large error between here and the actual prediction. In fact, it's a +7. Is that what we said? Somewhere between 90 and 90. Okay, so maybe not 96, but 97. So a residual of +7, and it's again a positive residual because the actual data is above the line. Here we have the triangle, another data measurement, and you see the line that the actual measurement is below the predicted line, so it's a negative residual, about 4 points, because this predicts somewhere around 94, where it's actually I guess this is like maybe 93, I don't know. It needs to be 4, so maybe this is 93 and 97. So residual is -4, negative because the actual measurement is below the prediction line. So -4 is a larger residual than -1, even though -4 as a number is smaller than -1. But remember, residuals, we're comparing the absolute value, right? There's a bigger error for this than there is for this point here. I've shrunk down my graph so we can do another example with residuals. This point here, marked with an X, that's an actual data point, a sample of one of the possums, with total body length of 77 centimeters and a head length of 85.3 millimeters. This is actual data. The linear fit is given to us by this equation, y equals 41 plus 0.59x. Based on this line, compute the residual of the observation 77 and 85.3. So here, our point xy is equal to 77, 85.3. The regression line predicts y equals 41 plus 0.59 times x. So our x is 77. So we plug that in, and we get then our y hat. This is our prediction, is equal to 86.4. So you notice our x is the same because we're given x and we're trying to predict y. We have our actual y, we have our predicted y hat. So again, our regression line then would say 77, 86.4. Our observation is 77, 85.3. So our observation is 85.3 minus 86.1. It's minus 1.1 units. So it's 1.1 units below the regression line. And we would say that our error then is negative 1.1. If a model underestimates an observation, will the residuals be positive or negative? What if it overestimates the observation? So if it underestimates, that means the prediction is too low. That means the observation is greater than the prediction, and we will get a positive residual. You can see here that the model overestimates, right? Our regression line said 86, but the observation was 85. And that means there's this error of negative. So that's a negative error, a negative residual. The same data, but now we're going to look at this triangle point, which is 85, 98.6. The linear fit given by the same line, y equals 41 plus 0.59x. Based on this line, compute the residual of the observation 85, 98.6. Here I have written our actual observation with xy is equal to 85, 98.6. What I want to know is what does our regression line predict for x equals 85. So we plug in x85 to get y hat. That's our prediction. Y hat is equal to 41 plus 0.59 times 85, which is 91.15. So the regression line says 91.15. The observation says 98.6. So 98.6 minus 91.5, that's 7.45 units above the regression line. Is that right? The observation is above the regression line. That means our error is 7.45. That's our residual. Because residuals are helpful in evaluating how well a linear model fits the data set, we often display them in a residual plot. The residuals are plotted on their own original horizontal locations, but with the vertical coordinate as the residue. So here is our original data set, our possum total length versus head length. Let's take a look at x. So now this residual, we had just calculated that. I should bring over those calculations. So the first residual we calculated was for this x point here. So on our residual plot, because the residual is negative 1.1, we're going to put for the x value. So we keep the same x-axis, total length, versus residual now instead of head. So for the same value of x, which is approximately, what is this, 77, we're going to have the residual of negative 1.1. This next residual, remember, that was the one that was quite big. That was the 7.45. So for this cross over here, which is near 85, our residual then value is going to be 7.45. So this is about 7.45. So this is our residual plot. Here's some more plots showing our original data with our regression line, and then here's what the residual will look at. Here we have another regression line. Data is a little bit closer, so we expect the residuals to be a little bit closer. Here, the line, the data is all over the place, so we're expecting more variation than the residuals. So you can see the residuals get to be higher. Also over here, you can see that there are points where the residual is very small, and that's over, in these points here, where the points are very close to the line. Our last topic is going to be about correlation, which measures the strength of a linear relationship. So correlation always takes a value between -1 and 1. It describes the strength of the linear relationship between two variables. We denote often the correlation by a capital R. And when the relationship is perfectly linear, the correlation is either -1 or 1. So let's draw a little graph. So correlation goes between -1 and 1, and somewhere over here is 0. So this is a perfect line going up. This is a perfect line. -1 is a perfect line going down. Here, there's no line, no obvious line. So as we move away from 0, we're getting more and more line-like. If it's negative, we're getting a downward sloping line. If it's positive, we're getting an upward sloping line. But again, as we move away from 1 or -1 towards 0, we get less and less of a line. If the relationship is strong and positive, the correlation will be 1. If it is strong and negative, it will be near -1. If there's no apparent linear relation, the correlation will be near 0. Also, we need to be careful. Non-linear relationships are possible, so a low linear correlation does not necessarily mean weak association, and we'll see an example of that in just a moment. So here are some examples of correlation. So let's start with the correlations that are near positive and -1. Again, as we get towards -1 and 1, we get this perfect line. These dots line up perfectly in a line. When we have the +1 correlation, we have an upward sloping line. In other words, as x increases, y also increases. Right? And then here, as we get towards -1, as x increases, right? So here's one value of x. Here's a larger value of x in yellow. The value of y gets smaller than the value of y for this larger x. We have this negative correlation. Now, when we go from 1 to 0, we're going to still have that upward slope, but more and less like a line. So here, as r gets to 0.98, it's still a pretty strong linear correlation. So there is very much a line, but not as strong as r equals 1. R equals 0.69, a little bit of this upward slope, but it's starting to devolve. And here 0.33, I would barely even say there's a line there. Let's do the same thing for -1. So perfectly downwards line, r equals -9.2, still strong linear sense, as it does look like a line, but it's a little loose. Over here, -0.64, even looser, and as we get really close to 0, it's just kind of a little cloud of points. And then our last warning, we need to be careful. Nonlinear relationships are possible, so a low linear correlation does not necessarily mean weak association. So you can look at these. These all have graphs, like this one is a graph. So I can write an equation for this parabola and for this cubic function that is actually a very good predictor of these points. Actually, this parabola should probably be higher up. But anyway, they're not lines, so we expect low correlation or low linear correlation. Here, this one, I don't know if it has necessarily a graph, but we do see kind of like these little clusters of things. So your book would say there's some sort of association, but it's not a line. Reviewing what we covered in this video, we're looking at an introduction to linear regression. We started by fitting a line to our data. So we try to predict a variable y based on a variable x. And our predicting line, is y equals b0 plus b1x plus some error. So b0 and b1 are parameters. They're just numbers, like constant numbers, times a variable x. From algebra, you know that this is the form y equals mx plus b, where m is the slope and b is the y-intercept. The next thing we talked about residuals, so the leftover variation in the data after accounting for the model fit. In other words, our actual data is equal to our line plus some sort of error that we call residual. The residual of the ith observation, x sub I, y sub I, is the difference between the observed response and the predicted response, again, the error. If an observation is above the regression line, then its residual, the vertical distance from the observation to the line, is positive. Observations below the line have negative residuals. And we use residuals to evaluate our regression lines. And the goal is to predict a regression line for the residuals to be as small as possible. And the size of the residuals is discussed in terms of absolute values because we don't want the negative residuals to cancel from the positive. Our final topic was correlation, which is a measure of the strength of a linear relationship. Correlation always takes a value between -1 and 1 and describes the strength of the linear relationship between two variables. And we often denote the correlation by a capital R. When the relationship is perfectly linear, the correlation is either -1 or 1, as in these two examples here. If the relationship is strong and positive, the correlation will be 1. So in other words, strong and positive, as x goes up, y goes up, the line goes upwards. If it is strong and negative, it will be near -1, as in this example. As x goes up, y goes down. In other words, a downward sloping line. So that's a negative slope. If there's no apparent linear relationship, the correlation will be near 0. So as we go from r equals 1 closer and closer to 0, you can see the points become more and more loosely connected until they kind of become just a cloud of points. And the last warning is nonlinear relationships are possible, so a low linear correlation does not necessarily mean weak association. And these are our examples. Here you can see there's definitely a pattern for the data, but it's a curve, it's a parabola. So our linear correlation is going to be low, even though there's a strong association with data. Here also there's this cubic curve that can predict this data quite nicely. But again, it's not a line, so our correlation coefficient will be low. And here we have some clusters of points that maybe we can predict, but it's not a line, so our correlation coefficient will be low. So that's it for this video. Thank you for watching.